Welcome to the AI Research Roundup. I'm Alex. Today we're looking at a paper trending on X, published on December 29, 2025, just 5 days ago. It demonstrates a new reward modeling framework that enables robots to jump from near zero performance to a 95% success rate with only about 1 hour of real-world practice. The paper is titled Robo-Dopamine, General Process Reward Modeling for High-Precision Robotic Manipulation. And as we'll see later, the system's ability to adapt to new tasks using just a single human demonstration is quite remarkable. And for those interested in the implementation, the authors have shared their code on GitHub. Figure 1 presents the complete Robo-Dopamine pipeline. On the left, the diagram illustrates the general reward model construction, which leverages a massive 35 million sample dataset to learn step-aware progress, visualized here with a pants-folding sequence. The flow diagram on the bottom right details how the system uses this pre-trained model for one-shot task adaptation and policy-invariant reward shaping. Finally, the charts in the top right highlight the performance gains, where the radar plot shows superior reward accuracy, and the bar chart confirms that this approach significantly outperforms standard reinforcement learning baselines. Well, while the previous chart showed the results, Figure 2 now unpacks the actual machinery, split into two main parts. On the left, Panel A details the reward modeling method. It takes multi-view images of the robot's state, specifically comparing before and after snapshots against the goal, and processes them through a vision language model to predict a progress hop. To make this robust, the bottom section shows multi-perspective progress fusion, which combines predictions from different reference points into a single, smooth reward curve. Then on the right, Panel B illustrates the training framework. It uses one-shot adaptation to tailor the model to new tasks and applies policy-invariant reward shaping, which is critical because it guides the robot efficiently without altering the optimal policy. So, putting that methodology to the test, Figure 3 tracks the reward signals during a tricky real-world insertion task. The film strip at the top captures the robot making mistakes, such as inserting the block incorrectly at step 40. In the graph below, notice how the yellow baseline model fails to spot these errors, maintaining a deceptively high reward score. In contrast, the blue line representing their general reward model drops sharply alongside the red reference signal whenever the robot falters. This precise tracking ensures the policy learns from its failures rather than getting false encouragement. Alright, while Figure 3 showed a single example, Table 1 provides the comprehensive quantitative proof. It compares the value order correlation scores, which measure how well a model understands temporal progress, across datasets like Droid and Libero. Notice the baselines on the left. G versus L and versus LAC often fail to track complex tasks, with averages hovering around 0.2. In contrast, the rightmost columns demonstrate that their multi-view 8 billion parameter model dominates, consistently achieving scores above 0.9 regardless of sampling density. Okay, while Table 1 focused on progress tracking, Table 2 asks a simpler question. Can the model correctly judge if a robot actually succeeded? The table reports classification accuracy across 60 real-world rollouts for tasks like stacking and folding. In the top section, generalist models like Gemini 2.5 Pro and GPT-5 achieve respectable averages around 80%, though they often miss fine details. In contrast, the middle rows show that prior specialized reward models perform surprisingly poorly, dropping below 40%. Ultimately, the bottom rows confirm that the author's multi-view model dominates with nearly 93% accuracy, beating even the largest generalist systems. So, accurate rewards are great, but do they lead to better robots? Table 3 answers this by comparing policy performance and sample efficiency across 10 simulation and 8 real-world tasks. First, look at the baselines in the top rows. Behavioral cloning, labeled here as BC, fails miserably in the real world, with a success rate of just under 10%. Standard reinforcement learning, with sparse rewards, improves this to 68% but is slow. In contrast, the bottom row reveals that Dopamine RL rockets the real-world success rate to 95% while requiring fewer practice episodes. Well, having established the high performance in the previous table, Table 5 now performs an ablation study to pinpoint exactly which design choices matter most. The top row sets the standard, with the full framework achieving an 85% success rate. Moving to the middle section, we see that disabling the multi-perspective fusion immediately hurts reliability. Relying on just a single view, like the incremental one, drops performance by 15%. However, the most critical finding appears in the bottom rows. Removing the policy-invariant reward shaping causes a catastrophic drop of nearly 44 points, proving that this specific shaping mechanism is the linchpin that prevents the robot from getting stuck. Wrapping up, 2 takeaways stand out. The general reward model provides precise, multi-view feedback for complex tasks, while policy invariant shaping ensures robots learn efficiently without gaming the system. These advances allow agents to master real-world skills in just 1 hour, paving the way for truly scalable robot learning. That's it for this episode of the AI Research Roundup. I'm Alex. Thanks for listening.